Hello friends, welcome to Bhugoal Khagol. Today we have with us Dr. PUNAM BEHARI ma'am. She is retired faculty from Department of Geography, Miranda House, and she taught there for almost 40 years.
40 plus, yes.
40 plus. You joined Miranda House in 1974, my God. And ma'am is a gold medalist in both her graduation as well as post-graduation.
Oh, wow. You know it all.
Yes, I know that. And she's the most loved teacher of Miranda House, and at least my favorite on the record.
That's very cute of you.
And ma'am has also been the vice principal of Miranda House.
Yeah, you're right.
And today, ma'am will be talking about the core of geography, which is maps, and not only maps but also map appreciation. So maps, as we know, represent a portion of the earth or the full earth in a 2D, two-dimensional sphere, not sphere, two-dimensional flat surface. But still, maps can be misleading sometimes. We may not be able to read the information on the map correctly, and it all depends on the projections, the scales, how we see the map. There could be error in creation of the map, or the colors, the symbols that we use. So ma'am will be talking in detail more about how to read a map and how to read it correctly rather. Yes.
Yeah, Akriti, you're right, because today we can't live without maps.
Yes.
And I think it's Google Maps which has brought us the meaning of maps. We can't navigate from one place to another without Google Maps.
Yes.
But the point is that we need to know more about maps and therefore understand how they are created. And that helps in appreciating them better, that what are their advantages, what are their limitations. If you know all those things, then you can understand, and I feel a better word for it is appreciate them better, because a lot of effort has gone into making any map.
Yes.
No map is, even if it's a digital map, it has a lot of effort gone into it. So it's extremely essential for us to understand how these maps are created. As you said, they are representing the earth. So what are the features on the earth that you are trying to represent onto a flat piece of paper or any surface, and then what goes wrong with them, what is distorted?
Yes.
So it's not, you can say that they lie, but they're really not lying. So you have to really understand how and appreciate them better. That's the aim today, is only to understand what are map projections and what are latitudes and longitudes on the surface of the earth, and what do they become on a map.
Yes.
And then how to use them when we want to, for whatever need we need.
Shall we begin the presentation? Yeah. Okay.
Okay, so just as we've said, maps are very powerful and fascinating tools, and like it's always said that a picture is worth 1,000 words, so a map is worth 1,000,000 words.
Yes.
But all maps distort reality. That's the sad part of it. They are not a picture, they are not a complete representation of the earth. All map makers have to use generalization, they have to use symbols, they can't make it to a one-to-one scale. And so the aim is to highlight critical information and suppress the details that are not required.
Not required, yes.
So today, as I just said, the term maps, everybody thinks of only Google Maps. The other maps are kind of forgotten, because we are using them every day to navigate our surroundings. And artificial intelligence is being used constantly. They change the speed limit, when is the shop open, all these kind of things. So in order to empower our understanding of maps, we need to delve a little deeper and comprehend how maps are created on a smaller scale for a larger area. Because when you're doing a Google map, you're just getting the road, turn left, turn right, this shop is here, your destination you've reached. But now what we have to look at is maps for larger areas maybe for the world, maybe for a country, maybe for a city, for whatever place. And technology is changing very fast, but the basics of cartography remain still very, very relevant, whether you're using software or whether you're using it yourself. You've got to understand the basics of cartography.
Yes.
Then only can you learn to
Yes.
make or even read maps. That is cartography. Cartography is the art and science of making and understanding maps. So it's not only for the students of a particular group who only want to make maps. It is cartography is essential also for us as a common layman to understand maps. So maps, as we said, are not perfect representations of the earth because you are converting a three-dimensional earth into a two-dimensional surface. So whereas the grid on the globe, as you see, and what it becomes when it is projected on a 2D surface. So the point is that you cannot flatten an orange peel, keeping it intact, right?
Yes.
This is the season to be having a lot of oranges, so you can try it out. You cannot flatten a whole peel on this thing. You have to make some tears.
Yes.
So, if you peel off the surface of the globe, it's going to have breaks, it's going to have tears. So there have to be some kind of distortion. So this process of flattening the earth will cause distortions in one or more of the following spatial properties. Either distance will get affected, areas will get affected, shape will get affected, or direction will get affected. No projection can preserve all properties. As a result, flat maps distort to some degree, definitely. Hence, it is essential for us to understand the size and the shape of the earth and the real world coordinates. We'll stick to the real world coordinates to evaluate the usefulness of maps. So, just for your information, map projection is a two-stage process. The earth, as we know, is not a round globe, it's a geoid.
Yes, it's a geoid.
Earth-shaped. Very nice term that we found. Earth is earth-shaped. Geography is what geographers do. So, then you convert that geoid into a ellipse. And then that is, the equator is longer and the poles, it's shortened at the poles. Then you convert it by geodesy. Geodesy is the study of the earth size and shape and all that, into a sphere, into a perfect sphere, and from a sphere into a reference globe. And on that reference globe you have latitudes and longitudes, which you then transfer onto a flat surface.
Yes.
So that is the two stages. First, when you're reducing the earth to a smaller scale, to a sphere and to a reference globe, and then transferring the parallels and meridians to a flat surface on a developable surface. So the question then arises is that if maps distort reality, why use maps? Why not globes? So globe is the only representation of the earth that does not distort the earth, but it's very inconvenient.
Yes.
Firstly, you can't reduce, if you have to show all details, the size of the globe would be so large that you wouldn't know how to go around it. So they're inconvenient to store, they're inconvenient to carry, they cannot show all kinds of things. You can't show climate on it, you can't show rainfall on it, you can't show natural disasters on it. It could be only a certain amount of information that can be given. Maps, however, are very easily portable. They can depict a wide variety of data, various themes, anything you can think of, you can make a map of.
They're dynamic.
Whether it's food, whether it's anything that you can make a map of.
Versatile.
So they show considerable details for smaller areas, and you can measure the area on it, you can calculate directions, distances. Everything is much easier on maps. So we can't live without maps.
Yes, we can't live without it.
So let's come back to our map projections. As we said, it's the process of projecting the spherical earth onto a flat surface, accomplished through a projection. So now map projection is defined as a systematic transference of the network of parallels and meridians from the earth, from the globe to the flat surface. So what we are transferring is actually not the continents or your area, you are transferring the latitudes and longitudes from the surface of the earth onto a flat surface. So we need to know the characteristics and the properties of the latitudes and the longitude. So map projections affect the way the map is made. So if on a map, if you put the paper in the form of a cone, or you or a cylinder, or as a flat piece of paper, it affects the kind of map you get. So you can see the different shapes of the maps that you are getting there, and that affects the kind of use that you could use it for. You could use it for equatorial areas or tropical areas or the polar areas, depending on what map projection has been used.
Yes.
So this is a little diagram which shows on the earth, this was the face of these masks, and this is what it becomes when you flatten it out onto a cylindrical Mercator's projection. And this is always quoted as an example that Greenland is actually 1/10 of the size of South America, but on this it looks so much larger, and we'll see how and why this happens. So the Earth's graticule is the critical foundation for understanding the concepts on map projections. So why does it work? Because to determine the exact unique location of any place on the surface of the Earth, we have these, we're talking of latitudes and longitudes, they really don't exist on the surface of the Earth, they are imaginary lines, and they form a graticule. The graticule is composed of the latitudes and longitudes and allowing points to be uniquely located on a sexagesimal system. That means all of them are measured in terms of degrees, minutes and seconds. So that's the graticule. It is latitudes and longitudes. It's the framework around which the location of the Earth's surface are recorded and analyzed with maps. Once you get your latitude and longitude, you get your place. Except for the poles, each point on the globe has a single latitude and longitude. This unique combination of intersecting latitudes and longitudes provides a precise location of a point on the Earth's surface. The conventional manner of referencing a point is first you say the latitude, you say north and south, and you say the longitude, which is east and west. For example, for India Gate, they say 28 degrees, 36 minutes, 45 minutes north, 77 degrees, 13 minutes, 52 seconds east.
Otherwise, they may also use negative sign
that is
for
the newer.
West and south.
Yeah. So latitudes are lines, imaginary lines of course, which are running east-west direction, but they are labeled as north and south of the equator.
Yes.
Because the lines of latitude never intersect one another, they are called parallels, since they are running parallel to each other. So what is that latitude? It is very simply the angle that is subtended from the center of the Earth. So you have the equator as your central plane because it is the largest parallel. It divides the Earth into two equal parts. It's a great circle, and the angle that you have between the latitude and the equator is what gives you the angle of the latitude. Right. So they are 90 degrees north and 90 degrees south. So it is the angle that is subtended north and south of the center of the Earth with the equatorial plane. So these diagrams make it a little clearer. So you have the center of the Earth, you have the equatorial plane, and the red line on top, that is the angle that gives you the angle of latitude. And when you cut the Earth like that, so they are angles from the equator, north and south, very simply. Latitudes are reported in angular measurements, as we just said. So we said it's a sexagesimal system. That means that each degree is divided into 60 minutes and each minute is divided into 60 seconds. That's why it is the sexagesimal. Major latitudes, as we all know, you have the Arctic Circle, about 66.5 degrees, 30 degrees north. You have the Tropic of Cancer, 23 degrees, 30 minutes north. You have the equator, which is a great circle. Great circle is any circle which divides the Earth into two equal parts. At the Tropic of Capricorn, 23 degrees, 30 minutes south. Antarctic Circle, 66 degrees 30 minutes south. So that again is another diagram which just tells you that again it is the angle which is coming from the center of the earth. So what is something more about their properties. The length of the parallels gradually decreases towards the pole. This is a very basic point that we all know, but we must remember when we are looking at a map. In the map, very often, all the latitudes are shown of equal length. So the equator, which is the great circle, that is the largest. And as we go north on south, they get smaller and smaller. The poles become just simple points. Latitudes are parallels, so the distance between them is also all the same, right? So these are the points to look for in a map projection. This information can be intelligently used while looking at projection. That what is the length of the parallels, what is the spacing of the parallels. So we just have an example here. Let's look at the latitudes on the very famous Mercator's projection. So what happens is the latitudes are straight lines parallel to each other. So far so good. But all latitudes are equal to the equator. So even the Arctic Circle is becoming equal to the equator. So there is so much of exaggeration as we go away from the equator that things get exaggerated. That's why the shape of Greenland is getting so large. So the distance between the parallels is also keeping on increasing. The distance between 0 and 10 degrees north and south is okay. Then between 20 degrees gets larger, larger, so much larger that the poles are infinitely exaggerated. You can't draw the poles on it. So the spacing is not equal. So the distance between the parallels increases towards the poles. Hence the projection is appropriate and should be used and can be used only for equatorial areas and tropical areas, because there the meridians as well as the parallels are correct. There is a little exaggeration, but not too much. But if you go on to the temperate zone or the polar areas,
it won't make sense.
It would be absolutely quite ridiculous. Right. So that's for our latitudes.
But we use Mercator's projection, a variation of Mercator's projection for these ArcGIS and
for everything. Today you have
digital mapping.
So Mercator's is a very wonderful projection. We'll come to see that later. But these are the points that you just must look into constantly. Longitudes run north to south, from North Pole to South Pole. They are here for the latitude. You had the largest equator. Now you don't. They're all equal. All latitudes are equal. They run from the North Pole to the South Pole. They're actually semicircular in their shape. So they have, historically, the prime meridian. That is the longitude that runs through Greenwich, the Royal Observatory, Greenwich in England, and they are called meridians. Longitude also, how do we determine longitudes? It is the angle subtended from the center of the earth from the prime meridian to the given longitude. So whereas the latitudes were angles north and south, these are angles east and west, the baseline being the prime meridian. So it's the angular distance east and west. They are reported in angular measurement, and they are also measured in the sexagesimal system of degrees, minutes and seconds. So this shows us, so whereas their latitudes were the angles the other way around, these are subtended from the meridional plane, passing through the place onto the prime meridian, 0 degrees and the center of the earth. Important longitudes. Now this is important because when we see a flat map, very often we see 180 degrees east and 180 degrees west. On the globe, however, there is only one
180.
180 degrees. Call it east, call it west, call whatever you like. So the 180th meridian, or sometimes known as the anti-meridian, is 180 degrees, both east and west. And importantly, however, the international dateline kind of coincides with it, not completely. The international dateline has to be and is zigzagged, because if the meridian is a straight line, it's a semicircular line, it'll pass through a country. So you'll say it's Sunday at your house and it's Monday in my house, and so we won't be coming to school or college any day declaring a holiday. So depending on the countries, and there are little islands on the Pacific,
Yes.
it's a zigzag line, which is known as the international dateline. So their shape and length, they are semicircular lines joining the two poles and intersecting the parallels at right angles. All meridians are equal in length. Their spacing. Now here they are different. All latitudes were parallel, so they were equispaced.
Yes.
Longitudes are furthest from each other at the equator, and they converge at the poles. At a given latitude, meridians are always equally spaced. If you take the equator, then all the meridians will be at an equidistant. If you take 20 degrees north, 30 degrees south, whatever, they will be equally spaced.
On that particular
latitude. Meridians converge towards the poles and diverge towards the equator. Right. So these are your longitudes. There are these angles. In yellow, if you can see, that's the how they are being subtended. And if you take a view from the North Pole, they seem to be like diverging straight lines, though they are actually semicircles, because the Earth is round. Yeah. Now, what happens to the longitudes on our famous Mercator's projection? Meridians are straight lines parallel to each other. Now, they have become, if you look at the meridians, they've all become parallel to each other, and you see that they are longer than the equator. What was happening on the real Earth? They were half the equator. The equator was a great circle, and this was a semicircle. Now they are almost longer than the equator itself. Hence, the scale along the meridians is exaggerated. The scale along all the meridians is exaggerated. They are spaced at an equal distance at each parallel, that is fine. And 180 degrees east and west are represented as two separate meridians. That would actually happen on any flat cylindrical projection. When you lay it open, you will have two edges. So this is the kind of distortion that comes in on Mercator's projection in terms of the meridians. However, I would like to say that this exaggeration of both latitudes and longitudes gives them correct shape, allows them to have correct shape on the thing. So the graticule, latitude and longitude, when they meet at right angles, they are forming little quadrilaterals, right? The quadrilaterals are getting smaller and smaller towards the poles. They are larger towards that is because the semicircles converge at the pole. So the area of quadrilaterals between any two meridians decreases towards the poles and increases towards the equator. Yeah, this is what I was talking about. As both the parallels and meridians are exaggerated, the area of the quadrilateral increases towards the pole. The area on the real Earth is decreasing, but here it is increasing because the distance between the parallels is increasing.
Towards the poles. It should be, ideally it should be larger near the equator to have correct representation.
So Greenland is projected as larger than South America, though in reality it is 10 times smaller. But the exaggeration, the plus point is that the exaggeration of both the parallels and meridians helps to maintain shapes and also direction. Mercator's projection is known for navigation.
Navigation.
Because you've exaggerated this, you've exaggerated that. So that square or that rectangle remains a rectangle or a square, and the direction also remains the same. That's the amount of exaggeration is worked out in such a simple, nice manner that directions also remain constant. So the question that we ultimately is that how to choose a map projection. So choosing a map projection is a challenge for cartographers. Appreciating these characteristics is critical for the evaluation of the projections. Features such as size, shape, distance, scale can be measured accurately on the Earth. Once projected on a flat surface, however, only some of these qualities can be accurately represented. Every map has some sort of distortion. The larger the area, the greater the distortion. So depending on the map projection, cartographers must decide what element of accuracy they want to preserve. What is important for that map? And this determines which projection to use. So there are millions, thousands of types of map projections, all sizes, all representations of latitudes and longitudes. So you have to choose what is right for you, what is it that you're trying to show.
What fits best.
Yeah, exactly.
Customize.
Yeah. So here we have Molweed's interrupted projection. At the National Geographic, they wanted to show the ocean floors. So what they have done is that they have to tear it up somewhere, the map. So they've torn it at the land masses because that was not important for them. What was important for them was the ocean beds. So the map is pulled apart at specific meridians to minimize distortion, and cartographers would emphasize on whatever you want to emphasize, you bring that out and suppress the other. So armed with this basic information, I hope all of you enjoy your journey with maps. Thank you.
So now I'm more curious. That is true. That there are maps for specifically made for military purposes. Then we have also heard about influence of Europe on map.
Mercator shows the sun never sets on the
Yes.
British Empire.
Yes. So in what ways, different ways, maps have been used and sometimes also misused to.
So we need to see a little bit more on the types of maps and maybe how they're.
Yes. What has been your experience teaching maps and map projections at Miranda House?
I've enjoyed it to the core, and it is an eye-opener because when you talk about these latitudes and longitudes, everybody seems to know, oh, we know all this, we know all this.
Yes.
But when it comes to making a map, if you ask them to draw a map, the graticule for a particular place and then fill in the map into it, the answer is that this kind of a thing does not exist on the atlas. So what in the world do you need the atlas for? When you've got your graticule, you've got the atlas to tell you what is the shape of the coastline between two parallels and a graticule. Do it. So it's an interesting exercise because we've been just doing rote learning of all these things. So I have also in the last few years started with making them draw squares of various size, making a cartoon character and then enlarging it.
Wow.
Or making that into a rectangle and then distorting it so that they understand the significance of a graticule. Today everything is so digital that they don't have to draw anything. So if you draw a small Mickey Mouse and put a 1 centimeter squares on it and draw another paper, you draw squares of 2 centimeters. The shape will be the same, it will just become larger.
Yes.
But if you make it into rectangles of 1 by 2 and then draw that same Mickey Mouse,
It will,
you know, it is like those mirrors you used to see in the melas where you become fat and you become thin, you
Yes,
become tall.
yes.
So that kind of a distortion comes.
Yes.
So these are the basics actually that we have to come down and understand, rather than, you know, just using them and looking at them and understanding them from atlases.
But when we see the atlases, there are various kinds of projections on which maps are prepared. Do you think like people even look at
So that's the time now. Now is to look into the left hand or the right hand corner and
Yes.
see what map projection they have been
yes,
made for on and why.
and why? Yes.
I mean, atlases would be using the right map projection for the right area. So if you're drawing it for a, you know, it's a map of South America, what projection has it done? So we had introduced a course on map understanding in BA program, where they didn't have to do any drawing or maintain any file, only learn about appreciating maps. So that was a big success, and then they were very keen and they drew little maps for different areas to learn and to understand, you know. They were given an area, they chose a projection and they drew it, and as a project, those were interesting times.
Do you think artificial intelligence, GIS and all this technology has somewhere ruined
I
the
wouldn't
basics?
say ruined, but it is essential. You can't live without it. Today, you need it. Let's face fact. Let's not say that you have to have that paper map which you opened like this and then you could never close it back to the right place. But understand how they are done. How, you know, instead of you know, what kind of information is coming on the. I think it's more essential now to understand what kind of information is coming on these maps.
Because I don't think anywhere they teach UTM in detail. We learn about Mercator's, we learn about basic projections, you know, conical, zenithal, you know. Now the syllabus is so condensed everywhere.
But they have the UTM. They had
do
it.
have.
I don't know now. But they had the UTM in principle, the principle.
Yes,
of
the
UTM.
principle.
Because that is what everything is working on
because
today.
when we use the software, we simply select it mechanically, you know, but we don't understand the science behind it.
So that's why start with Mercator, then go on to the understanding of the UTM, because that is the basic for all most digital maps today.
And I have heard about your famous class on orange and apple, drawing on maps on that, something. I'm so sorry we don't have it today, otherwise I would have done that.
No. That was just, you know, the BA program was very interesting classes, and so we did all kinds of things, draw on balloons and then try and flatten out the balloon, and you know. The more of kindergarten, more of kindergarten activity, but you know, it helps.
So we draw a graticule on a balloon, any round surface, say a ball or a balloon, or
a balloon is easier to prick and then say, okay, now try flatten it out.
Okay. So this is how we can actually begin to understand how we transfer the graticule from the globe to the surface on a 2D thing. Okay, and then why we need projections.
Why we need. And then which choice of projection.
Yes.
Which is the area that what is the property that you're trying to show? Are you trying to show directions? Are you trying to show distances, area, distribution of something? So those simple basics.
So I'm really thankful. I have always admired cartography classes, and I remember Gandhari ma'am, Sudeshna ma'am, and yourself. 3 teachers used to take. We used to have 3 files, you know, and I think that was the most amazing time I have ever had. the cartography classes. I just hope we continue
Definitely.
because
Because maps are very fascinating. Actually,
Yes.
any kind of map you pick up,
Huh.
there is something to it that you
Yes,
can.
yes. Now, the other day I saw there are some sketchbooks of city maps.
Okay.
Okay, just for coloring.
Yeah.
So maps are everywhere, and we should understand maps to, like you said, appreciate maps more, and that is how we begin to understand our surroundings.
Exactly.
Rather than just using Google Maps for place of origin to destination. This is the route, how we navigate. So there is much more we can learn from maps, and it gives you a larger picture, one, and it also gives you in-depth information. So they are very unique in that sense. So thank you so much, ma'am, for this very interesting, very basic, very intriguing lecture, and we look forward for more.
Thank you,
Yes.
Akriti. It was such a pleasure that you. I'm glad that you all thought of such a thing, and I hope give all the best. Carry on the good work.